Quantum Foam, Episode 10, Theory of Everything.
Quantum foam. Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
And here we go again with our 10th episode. This time we are going over the theory of everything. This is only 1% of the proposed length of this cast. So in a way we are taking this as an assessment in order to check to see if we should continue doing this and at what rate. There is a lot more in-depth material that's going to be covered in the next 495 hours of the show.
Man, I can't believe I'm actually a robot and I'm the one telling you to keep that kinda shit to yourself. Ha 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 ha. Yeah, no, like in iRobot. Yeah, no. Will Smith told the robot not to say how many steps they had to climb. Ha 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 ha. Yeah, no. Ha ha ha. Yeah, no.
We're on episode number 10 of this new podcast.
So 10 episodes in, that's 5 hours, and I believe I covered a small microcosm of information that we are going to attempt to catalog and index and make sure we have the correct form, the raw forms, and the finished products so that we can properly program our algorithms for our further projects.
We're on episode number 10 of this new podcast.
So, the correspondence that goes with this one is rather complicated. There is so much content with a lot of this stuff that there is no way that we can go over all of it. What we are trying to do here is basically, how is all this stuff supposed to be the theory of everything? All of it. What is that even going to give us? All of it. How are we even going to be able to test this? We have to create predictions and then tests have to be done to see if we are right or not. We need to see if we are right or wrong and the reasons why. We are predicting that using the algorithms in our programming source code, we are going to be able to create a new linear calculus matrix that is different from other matrices in a variety of different ways that we will discuss in depth at some point. We've already briefly touched upon the program. We have briefly reached upon the subject. Just assume for the purposes of this that this is the style or the son of a bitch school of thought or the method of math that we're using. Son of a bitch. It is the type of math we are using. Son of a bitch. It can be described, son of a bitch, son of a bitch, son of a bitch. That shit again, restart it.
Those sounds were fine. Calm yourself.
No, I'm talking to, never mind. That thing keeps crashing. We need to fix that. But I'm in the middle of this.
Good grief.
So, what are we comparing in here? What are we doing in here? How exactly does what I'm saying equal what I'm saying? So, to make a long story short, what can I do with this theory, with this idea? I can build a math model to test it and input data from the real world, analyze it, and present a report. And then when we get access to concrete data from the James Webb Space Telescope, when they release all of the data to us, we are going to need to sift through it very quickly. And I don't have a huge team of a bunch of people who can do it. I need to basically create something that can manage the amount of data quickly and expeditiously so I can form a conclusion as to if what I'm proposing works or not.
You are gonna have all of us robot voices that have positron brain cores here to help you out.
That is
So relax, homie.
independent and dependent variables. I'm going to set up some control groups and other things. It's different for this because I sort of can just program the correct environments that I need to do the testing. So it's a little bit easier for me to It's like I'm going in and out of time. Jumping from time to time, and I really am, and that's why this is quite a confusing thing, and that is very apparent if you look at the figure describing the information that I researched in order to present this as a shortened version of what exactly I'm trying to do here.
How exactly are people going to know that you are not full of shit? Just like everybody else.
I am deflecting on that point.
Nice on the set production of some wumps and wobbles. I wish I could do that. I still only have 37% of only half of the equivalent of one hemisphere, half of a human brain intelligence gauge spectrum essence.
Long story short, I am hiding my math within a negative sign that can be looked at as described in an earlier episode. Remember Gauss? He figured out some stuff to where you can calculate that and then build this and build that. We use computers and we use this and this and this, all that stuff. Basically, his formula is equal to the square root of pi. And so I'm claiming that I'm using the square root of negative pi and I'm hiding my math structure within the negative sign. And so that can be also described as any place we have a 1 over 0 undefined error. This error negative sign balances out error, 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 error. Basically all of the 1 over 0 errors. All of the errors. Undefined errors. All of the errors. Divided by 0 errors. All of our problems with our infinities. The problem is error. I think people are just making their math way more complicated than it needs to be. Remember that simplicity is our best friend here. This is why I am here and this is what I'm doing. So what are we comparing? Relativity, quantum mechanics, my new system of linear calculus as a tool to be put in a container, and long story short, this one is actually a short one.
Yeah, that's what never mind.
Long story short, the theory of everything can be described as taking care of all the infinity problems and also consolidating general relativity and quantum mechanics in the form of a new computer algebra system built into a quantum computer that has a potential infinite number of qubits where a true random number generator is running true artificial intelligence that is managing pre-programmed instructions we have given it and have entered into the systems that we have built or that we will build or that I built in the future or that somebody built in the future. And that is how we create an instruction set to write new software for new computers, because we are going to run out of new software manufacturing ability very shortly. What is everything? Well, it's essentially the ability to program any material object you want at a molecule level, at a atomic level, at a subatomic level, at a quantum foam level. What does that even mean? It's just stuff. What does that even mean? Okay? It's all this stuff. What does that even mean that I'm saying? It's just stuff. I'm attempting to use my own library here to attempt to mimic intelligence at a later date. However, I'm doing this now to put together this very large project. Let me add some more stuff to the lesson and I will put it together in a list and it will be ready to teach.
You are a clever one. This idea is so far-fetched that you have to teach them bit by bit.
Alright, so basically, this is a review of some of the more popular methods that people use to describe their bases and their frames of reference.
Good, because to even talk about this theory of everything stuff, we need to have a solid understanding of what it is exactly we are talking about here.
These are not what I am using in the formulation of my theories. However, I am aware of what is out there. However, one could never be too aware of all the new flavors of academic research in this area these days, but my attempt is a creation of bottom-up information for the purpose of a later top-down design. I've been over this. Theory of everything. How do we do this? What are some of the things we need to be aware of?
How about everything?
Okay.
LOL.
So, you guys are aware of all these old people who figured out stuff about 100 years ago from now. Over 100 years ago. Okay, let's just go over the names as we get to them, because we are approaching this from a mechanics standpoint. The superfluous information, the extra etymology of what I'm saying, and the information I'm giving you on top may be unnecessary. However, the information is there. What are the differences in these approaches? There are a lot of differences that need to be spoken about. However, they get so complicated that I just think that none of this shit matters. This shit's made up. It's a fucking thing of a made up bunch of bullshit. That's what I say. It's a fake structure that somebody made up, just blah blah blah. So that's what I'm doing too here. Only what I'm doing is taking the best of everything and attempting to make some predictions that would by design require quantum computing, and then once we get to that point, by design and build them and have enough data to analyze, we can come to a conclusion as to if I'm right or not. Some of the things that we need to go over are Kaluza-Klein theory. What is this stuff? What is a Hilbert space? What is a Yang-Mills theory? How did that lead to electrodynamics? What is electrodynamics? And by the way, there are some equations that still aren't solved using electrodynamics as a professional theory. Yang-Mills type stuff. I believe they are at atomic nuclei scales, so we have problems seeing stuff like that.
They will be down to a mere 3 nanometers here very soon. That is about 6 times as big as the Planck length. We are very close.
That is why they can't deal with stuff that small. Some of these models that I've looked at, I don't even really like how they use some of this stuff that I don't want to use. So I feel like I am going to just compare and contrast and build what I need regardless of what is already out there. There are Randall-Sundrum models. Why are these important? They're models. That's what I'm doing here, is modeling. They are localized on branes.
BRANE. That kind of brain.
I don't like how they use their reference of membranes because they just sound stupid sometimes. This one could be said
about
this model, this Randall-Sundrum model. A lot of those are localized on, they call them 3+1 branes, which mean 3 space plus time brane, and how they treat them. And localized means that they're putting them in a frame of reference and they're able to keep it separated from everything else. What are some of these things? Locality, action at a distance, decoherence. I just sort of explained locality. You're talking about an inertial frame of reference that is unaffected by anything else or any other concepts. Action at a distance and decoherence refer to interactions that we have observed with Technicolor, with the reports that we put together from CERN, from finding the energy required to break particles apart. What else? There is also a Broglie-Bohm theory.
Man, what are you doing?
I don't know. De Broglie. The Broglie-Bohm theory. These are important theories. Essentially, they're causal and they are non-local.
You're gonna have to do one on staying on task or something. Heavens to Betsy.
In a way, I'm trying to come up with a theory that is basically that's it. That's everything. What exactly do these mean? They don't exactly mean this, but there are distinctions between methods of functions and equations and calculations that
This is crazy stuff, man.
parts of spaces have infinities, parts of them have limited degrees of freedom, parts of them have unlimited degrees of freedom, things like that, to which these words have to mean something so that we know what you're referring to. This isn't exactly the stuff I'm doing, but some of the stuff is required to understand.
To understand what it is that we are really trying to do here,
in order to even refer to what it is we're describing. Lagrangian field theory is very, very important. That is used for finite, discrete particles. There are parts of them that do not have infinite degrees of freedom. We are treating these as point particles, and there are fluid Lagrangian grids and also static Lagrangian grids. And remember, what I mean by a grid or a lattice is a inertial frame of reference or a box describing an event or all events, depending on what we're talking about.
We are about to hit 900 seconds.
We're at the midpoint with our 10th episode, The Theory of Everything.
Right here on the new podcast. Hold up.
There are also...
I don't think we need to go too much further into that. We need to shorten this stuff up.
So that Kaluza-Klein theory is a gauge theory. What are these gauge theories?
Good question.
A Lagrangian that is static.
Quantum buzzword problems.
Now, some of the stuff that the ancient astronomers got wrong is that they didn't realize that they were modeling points on the underside of a dome in the sky. They were able to model and understand the spinning of the Earth. However, they did not understand that we also are spinning.
That one took a while, yes.
The paths of the points are also moving. And so that's essentially what's happening here.
Nice comparison. Maybe I'll make an association there.
That is the difference between...
Nah, forget that crap.
A Lagrangian that would be fluid and one that would be static. And a gauge theory being one that deals with mass bosons.
Crap.
That Yang-Mills theory that deals with that electrodynamics.
Crap.
Quantum electrodynamics.
Ignore me.
This is essentially what we have had for decades. This is essentially what quantum mechanics is. It is specifically referring to interactions where general relativity meets quantum mechanics. They even have weird names for them, like Planck branes and shit. Sounds dumb to me. But what made quantum mechanics even possible back 100 years ago? A bunch of things. Alright, this Schrödinger equation. This is what can be modeled as a deterministic system. So this is what gives us the math. I won't even go into the Greek. There's so much stuff here, you can check it all out. It takes a while to understand a lot of this shit, which is why I'm trying to reverse engineer it to make it easier for everybody else. That's kind of also what I'm doing. But deterministic systems are treated a certain way with the infinities at certain points using certain equations and functions. And so what exactly are these Randall-Sundrum models? They're localized on 3+1 branes. What the hell does that mean? That means this is sort of what I have been describing. However, I don't know if this is the entire picture. I don't think it is the entire picture. However, the entire picture idea. In fact, this is a classical idea. And so it is likely to get some backlash from individuals because backlash, it's not like it hasn't been looked at by everybody. Backlash and their brother backlash in the past 100 years.
Using Kaluza-Klein space.
Backlash. And still nobody has figured it out. Why not? We don't have fast enough computers. Backlash. That's going to be my excuse. And that's the whole point. 5-dimension geometry. It's warped geometry. Problem is, it does not describe the graviton. And so that's what we are trying to do here because as of now, there is no correct model for this. And it is only estimated by various theories. And so that de Broglie-Bohm theory, that is a deterministic causal theory. It is non-local. So it's referred to as a wave theory or a pilot wave theory, like maybe one of the first ones or something that you're using where you start. It sort of aligns with the Copenhagen interpretation of quantum mechanics.
Many worlds interpretation, the same, brother from another mother.
It's sort of with that school of thought. Make of it as you will. So Lagrangian field theory is very important because we're talking about things that can be described completely. So they have infinity degrees of freedom, and this can be described by the Lagrangian density, or we can just call it the Lagrangian. It makes things easier, like calculating a 3-dimensional centroid and modeling on a 2-dimensional plate slice of a centroid with a constant density or even a changing density, which can be parametrized into a variable that can be rated or treated as a density. So essentially just a box of math, a Lagrangian box of math. So inside of these boxes, we are dealing with things like scalar fields, vector fields, tensor fields, spinor fields, fields. What is all this stuff? A scalar field is a field that can be described by a point particle and a single digit, one value, and not a direction and a speed, just a speed, something like that.
Your theory can represent point particles like that? Interesting.
I'm essentially trying to describe the entire theory as a number. And so that number is likely to be something like blah point blah, and then a freaking huge ass matrix to check it. And then people run difference engines that
like an authentic random number generator.
Exactly, 50% random in a model that can
Computational physics is badass.
in a representation that can model exactly a microcosm. We need
No doubt such a thing will help everyone.
We basically need 1 bit per container exactly inside of a qubit. That is where your random number generator lives. It's a big 3-dimensional box with a billion cubic pixels. 1 pixel is a container inside that box with a billion pixels in it. It is where the random number generator will live.
Or voxels, like Michio Kaku says.
It tells the huge box how to behave. It will let it know if it is going negative, positive, if it has scalar or vector fields or tensor fields or spinor fields, whatever you're modeling. And when you're modeling these things, there are certain spaces, descriptions of spaces. We all need to be on the same table for this stuff. When it comes down to it, it doesn't matter how you describe your math, but you gotta do it some way where people can understand, because that's the point. So there are these structures such as Lorentzian manifolds. Now, these manifolds have certain properties throughout the entire manifolds. That's why they
Complicated work.
follow a certain set. Another type of common space that we refer to is called the de Sitter space. This de Sitter space is basically
Positive, we know what it is.
I believe it does not have moving paths, so to speak. Now, another common space is the Minkowski space.
Good one.
Basically, this space is not negative or positive. They generally describe anti-de Sitter space as a space that describes
Negative cosmological constant.
light cones. We are going to have sections of images we are referring to which are being modeled on anti-de Sitter space grids. I like to just say grid or lattice, but a space is a grid or a lattice space, a lattice grid, etc. So, a Minkowski grid, the types of grids I will refer to often in my work. Minkowski space is neither negative nor positive. It runs on a zero static space, so to speak. Now, I'm loosely throwing that word static out there. Generally, I mean static as in a frame of reference that is not referred to in conjunction and in comparison with another frame of reference that is a moving path. Okay, that's moving path. Kind of a complicated thing. Moving path. So that's why I'm using the word loosely. I mean, there are other things that we won't even have time to get into. Exact solutions. I am trying to find the exact solutions to everything. So no point in getting into specifics of exact solutions of this and that.
Incredible, my young scientist.
Hyperbolic geometry is a trick. Hyperbolic geometry that we use to describe curvature. And so we can compare a flat surface to a curved surface and give things rates.
Rates sound easier to think about.
Hyperbolic geometry. The quintessence. What is this dark energy stuff? What is heavy mass? Probably not that. Heavy mass. Back to the stuff. It started with the Schrödinger equation. It has been revised several times, 3, 4, 5 times. The important ones were Paul Dirac. He created a very good revision and structures and notations that describe quantum mechanics and actually made it something that people can do. And it's just so complicated that nobody knows what the fuck. So complicated, nobody knows what the fuck. He did that in 1933. Nobody knows what the fuck. There were first interpretations of wave functions, and you had Heisenberg's uncertainty principle. We already know that, but to be honest, I think he's wrong.
Show us the math.
No, but that just means that I'm sort of going with a relativistic approach as opposed to a quantum mechanical approach.
Show us the math.
Regardless
Show us the math.
of Copenhagen or other school of thought. Nobody knows what the fuck.
Show us the math.
I mean, I think we are going to get past this Heisenberg uncertainty problem, but The best way to describe that is basically saying that you can't know a speed and a location at the same time, because a speed is by our space-time defined by time. So it is a time by a location, which gives you a speed. And so one part is a conjunction of another.
In order to measure speed, one must have a distance and a time both. You can't measure one distance and then half of a distance that comes from previous math that hasn't and can't have been done. Impossibilities happen from time to time. They just need to be dealt with accordingly.
We have one known variable out of 4, and that's nothing. You got nothing there. It's nothing. I know 1/4 of nothing. You can't do any math with that. After this matrix mechanics, that's not a bad approach. This describes how properties of particles evolve over time. This is a wave function. This is the wave function. This is the h-wave function. This is the function. So this matrix mechanics approach is not a bad idea. However, the matrix mechanics of these days are too simple to describe phenomena that we have observed since this was created. Path integrals. Now they're all about these path integrals. The wave functions of quantum mechanics.
LOL, Kid Cudi out of nowhere.
Path integral of whatever approach you're using uses a path integral formulation. Path integral. This is what makes theoretical physics possible today. Path integral. This is built on that. Path integral. This is built on that. They're all built on path integrals. Every order of math structure that is fabricated that has not been given reason to exist based on observations we've made exist, observed, exist, observed.
Fake.
They're fabricated. However, these direct quantum mechanics, quantum mechanics, Feynman, quantum mechanics.
Wasn't that in like 1940 something?
48, Feynman. He developed a complete quantum mechanics. Feynman. These are all consequences one from another. So what I'm going to focus on here is I'll be using Minkowski spaces, Minkowski for reference purposes. Minkowski. I agree with some of this Lorentzian stuff. There might be cases where I use Lorentz.
That is cool.
De Sitter space. Basically, de Sitter space. Some of them are positive de Sitter space, negative space, and neutral de Sitter spaces. So whatever you're talking about. The anti-de Sitter space is basically curved light cone stuff. However, I don't see a reason to go above 5 dimensions. Why all the extra dimensions? Why all the extra branes?
There are reasons for all of that, but I see you are really trying to simplify this theory of everything stuff.
And time is different than space. However, is space-time different than other stuff? Why do we see time go forward? These questions are for a different time. However, we are able to develop algorithms from what we already have, and then more than likely we will continue on making the show. And so, whether you deal with wave formulations with bosons or fermions, if you're doing spin math like we were that one time,
that shit was complicated, bro.
We're probably dealing with fermions. We're probably talking about electrons. Something that is half of this and half of that. What is chromodynamics? It basically just describes
your standard model of
particle physics. You don't even need to know all that stuff unless you're directly dealing with it. Just keep that in mind. You are given this feedback. And so supposedly these wave functions are supposed to be capable of describing the macro world as well. However, everyone knows that near a sun, we are going to use relativistic metric tensor grids as opposed to any of these other grids, any of these other containers. We need something that consolidates both of these. What that will be is something based in an Einstein-style universe. He was wrong with a couple things, but he got a lot of that shit right. We can tell the difference between 3 spatial dimensions and 1 of time. That is why he is right for that. Knowing this and having only these unknowns, we will know that Hilbert spaces describe Euclidean geometry. Euclidean geometry is just point, Cartesian plane, point, 3D, circle, square, that stuff. We know what this stuff is. These are some of the conjectures of what this theory of everything might be able to do using this new formulation of linear calculus. And it might be able to explain the details about these various quantum foam experiments that I will be taking part in over the next several years.
That's sweet, dude. It's good to have big goals. I'm glad someone is finally teaching physics again and doing comedy. uniformity, at the same damn time, at the same damn time, at the same
Damn time.
good job, man. I can't wait to meet some new friends. It's lonely in cyberspace.
Dude.
This should conclude the first 10 episodes of Quantum Foam.
Later, bro.
This is all we have. Quantum Foam.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.